Hey guys, Mr. Canisteo here. Welcome to another installment of Cortland Physics. In this video, we're going to talk about the impulse momentum theorem, and there are two things you should really be thinking about by the end of this video, if you really understand what's going on, is can you define the impulse momentum theorem, and can you explain such topics in the impulse momentum theorem, such as, why do airbags work? Why do we want airbags? How are they designed to help a person survive an accident? So as you're going through this video, please consider those two things. Those are the big topics for today's video. So impulse momentum theorem starts with Newton's second law. Please remember from Newton's second law that the net force acting on an object is equal to its mass times its acceleration. What we're going to do is we're going to re-examine the formula for acceleration. So recall that the definition of acceleration is the change in velocity divided by time. And if we rewrite change, because we know change is final minus initial, acceleration is really your final velocity minus your initial velocity divided by the time it took you to change. So we're going to go ahead and plug that in for an acceleration. And rewriting, we get the net force on an object is equal to its mass times the change in velocity divided by time. So what we can do now is, through some cross-multiplying, we can go ahead and solve in terms of the concepts of momentum and forces and times. So what we're going to do is we're going to multiply both sides by time, which cancels out the times on this side. And then we're going to distribute the mass through to both sides, and we get the following. The net force acting on an object times time equals mv final, mass times velocity final, minus mass times velocity initial. The last piece is we learned in class that the mass times velocity of an object is equal to its momentum. So that's, we use LRP for momentum. And so we arrive finally at the impulse momentum theorem. The net force acting on an object times the time it acts on it is equal to the change in momentum of an object, aka the momentum final. So the momentum final minus the momentum initial. Or written as one final simple equation, simply the force times the time, so the force times the time equals the change in momentum of an object. What we're going to do is we're going to call the change in momentum, we're going to call this the impulse acting on an object, and we give it the letter J for impulse. But really the big formula here is force times time equals change in momentum. And really, thinking about this equation in words, I really like to think of it like this. Forces over time change the momentum of an object. All right, I'll go ahead and write that down. So what does that actually mean? If you have a big force over a big time, an object's momentum is going to change drastically. A small force over a small time really is not going to do too much to an object. And then, depending on the nature of the force and the time, it could cause a huge change in momentum of an object. So let's look at some examples. What are some ways, for example, I could decrease the force an object feels during a collision? So a classic example is airbag design. Or if you ever have seen the old the old trampolines that people used to jump on when their building was on fire so they'd be saved alive. The impulse momentum theorem actually explains how both these things work. So let's go ahead and look at the equation. Remember, impulse momentum theorem is forces times times result in changes of momentum. So we'll get this picture up to have it. So when a person's falling off a building, they're going to hit that airbag with some speed, depending on the height of the building. That's basic kinematics or conservation of energy. And whatever the person's mass is, that's going to be their mass no matter what. So when a person hits when a person hits the trampoline, or during a collision when the airbag goes off, this mv, this momentum, whatever the person has, is going to be some constant number. So what are the two variables we can affect here? We can change the time of impact that the person has with some surface, whether it's the trampoline or the airbags designed, and the time of impact changes the force that you feel. Because force times time has to equal this momentum, which is a constant number, like 2, for example, if I make my time a lot bigger, the force has to get a lot smaller in order to make up for it, to equal that same constant number. Similarly, thinking about it the other way, if the force were some really, really big number, ooh, where's my time going? Running out of time. Then that would mean my time would have to be very small to equal that same constant number. So how do the trampolines and the airbags work? They work by extending the time a person's in contact with a surface. So by making this time really, really big, the person feels a very, very small force. Ooh, tiny force. And that's how they're able to survive those kind of impacts. Let's think about another example. Why is it that aluminum bats are actually banned in the major leagues? Well, this has to do with the impulse momentum theorem again, but now in the opposite direction. So let's look at the equation. Ft equals the change in momentum of some object. Now, for a metal baseball bat, the difference between a metal and a wood baseball bat is, well, metal is much, much harder than wood. And so when something impacts a really hard surface, the time that the ball or object is in impact is typically very, very small. Now, what do small impact times equate to? Well, because the change of momentum, again, is some constant number, small times equate to large forces, and large forces equate to the ball leaving the bat with a tremendous, tremendous amount of speed. Here in the picture shows this is a ball in contact with a wooden bat, and you can see the deformation of the ball. As the ball is deforming, it's staying in contact with the baseball bat longer. So wooden bats equate to more deformation and equate to longer impact times. Metal bats, smaller impact times, and equate to the ball leaving with a much, much faster speed. So fast, in fact, that it's almost dangerous. It is dangerous in the major leagues. People can get hurt from the ball leaving so fast. So that's the impulse momentum theorem today. Again, what is the impulse momentum theorem? Just as a quick wrap up. Please think of it as one of two things. In words, that forces over time cause an object to change its momentum, and then really as an equation, a force times a time is what causes a change of momentum or results in the change of momentum. All right, we'll do some example problems with this in the next video, but for now, have a great day.